will tell us about entanglement dynamics. Take it away, Brian.
All right, great. Thanks. Nice to see you all out there. Hope you're having a great meeting so far. It looks like quite an exciting set of topics. And yeah, I am going to talk about entanglement dynamics in this set of 4 lectures this week. That, as you can imagine, is a very, very large topic. So I've chosen to talk about some of the basics that you can take with you and apply to your problem of interest. That's mostly today. And then for the bulk of the lectures to focus on the dynamics of entanglement in the context of highly excited states of extended systems, which are what we would call quantum chaotic. So basically how systems generate entanglement as they approach an effective notion of thermal equilibrium. That's kind of the broad topic of these lectures. As we'll get into a little bit later, this has to do with all kinds of important questions in condensed matter physics, in quantum information, but also in the context of gravity and ADS-CFT. So it touches on many different areas. And I'm just going to try to give you the sort of bare bones, simple theoretical picture for how we think this can be described in the simplest possible cases. And I'm happy to give you references to more elaborate situations and to answer your questions, etc. So please interrupt whenever. And yeah, the rough plan is today I'll talk about foundations. So that's his first bullet here. Then tomorrow we'll discuss the effective theory of entanglement growth for quantum chaotic systems. This is still to some extent a conjecture theory. I mean, it definitely applies to some cases, as I'll discuss, but the extent to which it applies to sort of every quantum chaotic system is an open question. Then in the third lecture, I'll likely talk about information spreading, which gives us a different point of view on what is happening during entanglement growth. And then for the final lecture, I thought I would discuss some frontiers. In particular, I thought I'd focus on something that has come to be called the measurement-induced phase transition, MIPT, which is an interesting phenomenon that occurs when you combine unitary dynamics with quantum measurements. So this is a very hot topic in condensed matter and quantum information right now. It's probably something you're less familiar with if you have a high energy background, but I'll just sketch out, my plan is to sketch out the basics of that and give you a flavor of sort of what people are doing, like literally right now. Okay, so that's the plan. Let's go on to lecture 1, which is foundations. So I'm going to rely on the previous discussion of quantum information to some extent, but here's the basic setup. We're going to have a bipartite quantum system. This system has a Hilbert space, H, which is the tensor product of the Hilbert space of some subsystem A and some subsystem B. So the dimension here is equal to the dimension of A, which I'll denote D sub little a, times the dimension of B, which I'll denote D sub little b. Like that. And moreover, there's a basis for this space, which includes a basis of states in A, tensor some other basis of states in B. Right? So this, I presume, is sort of basic quantum knowledge that you possess. If you don't, feel free to message me or let me know, and I'm happy to provide you some primer offline. And this is the basic setting of entanglement. So entanglement is about correlations between different pieces. In this case, we're going to talk about correlations between A and B. Now, if you have a big quantum system with many parts, this choice of how to break it up into A and B is something that you get to choose. So different choices may be dictated by the physics. For example, A and B may correspond to 2 distant regions that can't exchange quantum information. They can only communicate classically, for example. In such a case, entanglement would tell you about what sorts of quantum tasks you can accomplish with that shared state. But in the context of many body physics, for example, or quantum field theory, we sort of choose A and B in a way that suits us so that we can extract interesting information about the quantum system, about the quantum state. Okay, now we say a state psi AB is entangled. This is, again, mostly probably review, something you've seen in quantum. Oh, whoops. Is entangled if it's not equal to some phi A tensor phi B. Okay, so if there's just no pair of states on A and B separately, for which you can tensor them together to get AB, then we say that this state psi AB is entangled. And this is a pretty generic situation. Most pure states are entangled. You can think of that just by counting parameters. The number of parameters that it requires to specify two product states is basically dA complex numbers here, that's the amplitudes, dB complex numbers there. But the product set of numbers are a special structure because they're products of these separate numbers. So the general basis coefficients, if you expand this out, will have some structure that's not captured by this product form. And so that's why this is, just from a counting of parameters point of view, a very special class of states, the unentangled states. Okay. So as a consequence, if I compute the state rho A, which is the reduced state on one of the subsystems, then if psi AB is entangled, this implies that rho A is a mixed state. In other words, although I know the state of A and B perfectly, it's in a pure state, I have maximal knowledge about that. When I have entanglement between A and B, the state of the subsystem is not, it's not possible to know that with maximal knowledge, which is what it means to be a mixed state. And this is just saying colloquially that A being entangled with B means that the state of A is somehow correlated with B. And so you can't assign independent pure state just to A. You have to know the whole state of the system to really find the purity. Okay. So next thing I want, and again, if there's questions, just interrupt.
Can I ask a question really quickly?
Please.
So entanglement is quantum correlations, but I know that like a mixed state is like a mixture of classical correlations. So what are the different possible parts of this mix?
Yeah, that's a great question, and actually a tough question. So in the case where I assume that this state is pure in the big system, then I compute this rho A, and basically all of these sort of measures of entanglement that or measures of entropy, say, that we're going to define in a second for rho A, which measure, those all just cleanly measure entanglement. If the initial state, if this psi AB is itself a mixed state, then it's much harder to decide sort of what counts as correlation, classical correlation, and what counts as quantum entanglement. In fact, this is, I would say, essentially an open question. Like, we know examples, but there's not even, for maybe for 2 qubits, there's a more or less complete characterization. But even for, pairs of slightly larger dimensional systems, we just don't know. All right, so there are criteria, which I'll discuss later, for when a state's entangled. But sort of the complete story here is not easy to answer. So it's an important and good question. Okay, so let's talk now about how to diagnose. Okay. What we're going to use is something called the Renyi entropy. And the idea here is if rho A is a mixed state, then I should be able to compute some measure of the probabilities in that state, something that tells me about their spread. And that's an entropic height quantity. This Renyi entropy is defined as follows. It involves a number alpha, which can be from 0 to infinity. And the alpha Renyi entropy on a density matrix rho looks like this. There's a prefactor, and there's a log, and I take the trace of the density matrix to the alpha power. Okay. So I take my density matrix, I raise it to power alpha, I take the trace of that, then I take the log of that trace, and then I divide by this prefactor. And the important fact is that S alpha vanishes if rho is pure, and it's greater than or equal to 0. Let's say it's greater than 0. Otherwise. So in this case, where the whole system is pure and the subsystem is in this possibly mixed state, any Renyi entropy for any value of alpha is a good diagnostic of that entanglement. It tells you, first of all, is the state entangled? And second of all, it gives you a number that you might want to call the degree of entanglement. And now there's many identities. One identity which is useful to know.
Just a question.
Yeah, please.
In the previous page, was the if and only if? As in, if we compute the Renyi entropy for some alpha and it's 0, if rho is pure, then does that mean that any alpha will vanish?
Yeah, if rho is pure, if it's a rank 1 projector, then it just vanishes.
Okay, and we just have to check for one alpha, and that's good enough.
That's right. Yeah.
To tell that it's okay.
This is an exact statement, so but yeah, I think that's a correct statement. You can choose any of them, and if any of them are 0, then it's a pure state. One useful identity is yeah.
And if one Renyi entropy vanishes, every Renyi entropy automatically vanishes as well. It's not possible that one vanishes and the other ones don't.
Yeah, I think it's not possible.
Okay, thanks.
So one partial proof of that, at least in one direction. So you have a bound, first of all, that the alpha Renyi entropy is greater than the beta Renyi entropy if alpha is less than beta. So make sure you get this, the relative sign here, right? So for example, S of 0 is greater than or equal to S of 1, which is greater than or equal to S of 2, which is greater than or equal to S of infinity. Yeah, and so you can see here, if say any of the S's of 0, all the higher Renyis are automatically 0 from this identity. And if you go back here, if you know that trace of some higher power is still 1, which is what this tells you, then that's sufficient to tell you that it has to be a pure state. Okay, so there's some special values. Of alpha. S naught is called the Hartley entropy or the max entropy. And you can convince yourself that it's the logarithm of the rank of the density matrix. So it's called Hartley or max entropy. This is a very crude bound. It's just telling you how many non-zero probabilities are there, and each of those contributes a unit amount to this quantity, to the rank, and then you take the log of that. S1 is minus trace rho log rho. This is what you get if you take the limit as alpha goes to 1. So if you go back to this formula here, you look as alpha goes to 1, well, this quantity in front is diverging. I'll let the slides catch up. This quantity in front is diverging, but trace rho is 1 by normalization. So the log of 1 is 0, and you need to take a limit, right? And if you take that limit carefully, it's not too complicated. You'll find that at alpha equals 1, you get this very special combination minus trace rho log rho, which is called the von Neumann entropy. And sometimes in the context of entanglement, called the entanglement entropy. This is the S2 is another important one. It's called the log of the purity. So trace rho squared is the purity, and the log of that is the second Renyi entropy. And then I'll mention one other special case, which is S infinity, which is minus log of the probability of most likely outcome. That's called the min entropy. I don't have space to write it, but anyways, the names will be written in the notes that I'll share after this. So of these, S naught, S1, and S infinity satisfy many nice properties. S1 especially is particularly nice. Theorists love S1. This is the quantum analog of the Shannon entropy, and you should have met this object in Patrick's lectures on quantum information. S2 has less nice theoretical properties from a sort of information theory point of view, but it's much more accessible. So S2 is a thing which can actually be measured in experiment. S2 is something which is relatively easy to calculate in a variety of models. So a great deal of our intuition for these quantities is related to S2 and related quantities. But in some cases, we also know these various other quantities. Any questions about those examples? I'll give you some actual calculations of these in a second, but this is where we are now, right now. Okay, so let's talk now about the relation to psi AB. Okay, so there's something called the Schmidt decomposition. Which says the following thing. So if state is unentangled, then we can write it as a product state. If a state is entangled, that's not possible, but we can also write it as a sum over product states in the following way. So we can write psi AB is sum over I from 1 to a number I'll call chi, square root pi and what are these? These are orthogonal states. on A and B. We can take them as elements of part of an element of a basis on A and on B. And I can always choose these states so that the coefficient is real. That's something I can do. I just absorb any phase into those states. That's certainly a totally valid thing to do. And this is always possible to do for any pure quantum state on any bipartition. You can always write it in this way. This is just a math fact. You can prove it using singular value decomposition, but just take it from me, it's a fact. Okay. And the consequence for rho A is the following. Rho A can be written as the sum over the same set of things, 1 to chi, of pi times these projectors. And here the sum, again, from normalization, the sum over I of pi. So this Schmidt decomposition is a nice way of viewing the full state, which then gives, which is written in terms of a set of data, probabilities and states, from which you can easily deduce the reduced state on A. And there's a corresponding expression for the reduced state on B, which uses the phi tilde IB states. Okay, and let's do it just a calculation. Here's an example calculation using this form. Suppose I want the S naught of this rho A, right? Well, that's going to be equal to 1 over 1 minus 0, the log sum on I, 1 to chi, like that. So again, this is alpha, that's alpha, that's alpha. And you can see here, well, any number to the 0 is just 1. And so this is just equal to log chi. So chi is just the number, it's just the rank of this matrix, and S naught, the Hartley entropy or max entropy, is the log of chi. And this is the biggest that any of these things can be. Remember, recall that S naught is greater than or equal to S alpha for any alpha. So the absolute largest value that any of these Renyi entropys can be is the log of the rank of the state. Just some notation, these PIs are called, well, really these square roots of PI are the Schmidt values. And the point here is that we can think of S alpha of rho A as equal to a classical entropy of the probability distribution PI. And what are these PIs the probability of? They're the probability that the subsystem is in state by the.
Can I ask a question?
Yeah, please.
What's the, I think I missed it. What's the reason why alpha has to be positive or 0?
Oh, I'm just saying that that's where I define these quantities for.
I see.
If you want to define them more generally, that's something that you can do. I mean, in particular, Let me answer your question here. So as an aside, I'll just say it's interesting to consider trace rho to the alpha as a function of complex alpha. So basically what I told you so far is we're looking at like on the real axis, but actually it's quite interesting to think of this as a function of complex alpha. It has a nice analytic structure in, say, the half plane specified by the real part of alpha being greater than 0. And that complex structure is actually very helpful. For example, it tells us that you can prove a theorem that says, if you know trace rho squared, trace rho cubed, trace rho 4, etc., you know all that infinite set of data, then you know the entire spectrum under suitable conditions on the growth of the spectrum, etc.
Brian, can I ask a question about that actually?
Yeah, please.
I've always wondered about this. So you need to assume these things about sub-exponential growth in various directions in the right half plane. Is that something that we have to impose by hand when we want to make the replica trick work? Or are there like general conditions under which we should expect trace rho to the alpha to have the analyticity properties needed to apply Carlson's theorem?
Good question. Yeah, let me think about that and try to offer a precise set of conditions. My intuition, my experience is that it's just almost always the case that it would in principle formally work.
Mm-hmm.
The issue, as actually I'll point out in a second, is that Carlson's theorem really only applies if you know the values exactly. So technically any error in your knowledge can have a disastrous impact on the analytic continuation. So I'll show an example in a second where every ring entropy except the first one is like S2, S3, etc. They're all very small, but the S1 is nearly maximally entangled. So somehow you need to know them, but you actually need to know them very precisely, which is something that if you have some experience with analytic functions won't surprise you. But yeah, the conditions for Carlson's theorem, I think, are pretty mild from
I guess this is just a polynomial, basically.
Yeah.
And
if it's a finite dimensional system, then it's just trivial. And
Right.
even an infinite dimension, like the growth at infinity is not a problem because it actually is a decreasing function. And in the complex, like in the imaginary axis, you need some growth condition there, but it actually doesn't grow. So I think it's pretty general.
Cool,
But
thanks.
let's come back to that later. Just as an example of this kind of thing, suppose your state rho is a thermal state, like this. Then rho to the alpha, if say alpha were u plus IV, this would be e to the minus beta UH minus I beta VH. So this is like actually some real-time evolution because you have an imaginary part there. So knowing this is a function of complex alpha can tell you about the spectrum, but also about time evolution with the log of rho, which is an interesting quantity. All right. So let's talk about examples. That was all pretty dry. Let's look into something a little bit more interesting. So suppose, as my first example, let's just consider this case where dA equals dB equals n. And psi AB, all right, as 1 over the square root of n, I equals 1 to n, I. This we call an entangled pair or Bell pair. It's actually maximally entangled. And you can compute, let's compute trace rho to the alpha. Well, rho A from the Schmidt form is just 1 over n sum over I equals 1 to n I. That's equal to 1 over n times the identity matrix on A. Right? And so trace rho A to the alpha, it's very easy now because all the probabilities are the same. So every single probability is 1 over n, and this is just n times n to the minus alpha. And now you plug that into your formula, and you just get log n for all alpha. So this is like the nicest, simplest case where every radiant entropy agrees. And it's because you have a probability distribution which is sort of maximally ignorant about the state of the subsystem. So the simplest place you ever encounter this in your life is probably the singlet state when considering angular dimensional addition of 2 spinets. Okay, let me talk about another example now. And this example is, as I sort of intimated before, a lot of information we have about entanglement comes from studies of second Renyi entropy, and a few cases where we can also access the von Neumann entropy. But this case is going to just be a sort of cautionary tale to let you know all this doesn't seem to occur in practice, whatever that means. It is possible that the Renyi entropy can be very misleading. So here, let's consider a case where dA equals dB equals n plus 1. And the psi AB is going to be defined like this. There's a new parameter epsilon. I have 1 over n, sum over I, 1 to n. So that's the same bell pair on the first n degrees of freedom. And then I'm going to add to this a square root of epsilon, n plus 1, n plus 1. So just take the bell pair or the entangled pair on the first n states, and then I append with a small probability this epsilon. Now you can compute again what this trace rho of the alpha is, and you'll find that it's equal to 1 minus epsilon n to the 1 minus alpha plus epsilon to the alpha. And now we see something kind of funny, because we have to ask which of these two terms is bigger. Is it this term or this term? And if epsilon is 0, then you just get back to the case we had before, where it's log n. But if epsilon is small, but not so small that it compares to 1 over n, 1 over the Hilbert space size, say epsilon is just 10 to the minus 3, but n is 1,000,000. Right? Then actually this term can dominate. We have if second term dominates, then S alpha is roughly 1 over alpha log epsilon. Plus order so it should be n minus 1. So this is sort of a little bit weird, because what you can arrange is for this to be a very small correction. Suppose this is a very small correction. Then this Renyi entropy for any alpha for which this approximation is good is going to be just some order 1 number. It doesn't depend on n at all. So n can be as big as you want. But this higher Renyi entropies are all just fixed numbers independent of n. But S1 you can easily compute is equal to 1 minus epsilon log n plus some subleading thing. So there's nothing wrong here, and it's true if you know all the Renyi entropies exactly, you can still, via this analyticity that we discussed previously, figure out what S1 is. There's no inconsistency, but it just means that you need to know them very precisely in principle. This is a contrived, strange example where if the dependence between epsilon and n is just right, and it's not too hard to achieve, then the Renyi entropy can be very small, but the binomial entropy can be very large.
Ryan, can you clarify where you're saying log epsilon is small? So epsilon is
Sure.
like 1/10. Log epsilon can be huge.
If you know, I mean, it's log 10. I wouldn't call that huge.
Wait, sorry, but epsilon. I see. Okay, sure.
Okay, can I ask a question?
Yeah, please.
This S1, if you put alpha is equal to 1 in your first formula, isn't it trace of, I mean, S1 becomes log of 1, that is 0?
Yeah. So the key thing is that this is, you can think of this as the limit, as alpha goes to 1 of 1 minus alpha.
Okay, I see. This is
Right,
the
so
correction
indeed, as you
to
say,
alpha is equal to.
This is 1, so that's 0, but this is divergent. So you need to take the ratio.
I see.
So just somehow it doesn't really occur in practice, as far as I know. But in principle, if you're computing these in some approximate way in your favorite theory, or your favorite situation, it's possible, we can't rule out unconditionally that S2 can give you a very misleading estimate of S1, for example. Like not just off by a factor, but scaling differently with the Hilbert space effects. And this is a repeated theme in this business. Like S1, the binomial entropy satisfies many, many nice properties. Many inequalities, strong productivity, you may have heard of these things, etc. S2 and S3 don't have any of these properties essentially in the generic case.
Brian, can I just ask, so how does that chime with this measurability of S2 being more easily measurable?
Well, it is measurable, but what's really measurable is trace rho squared, the purity. And if S2 is large, then that's already very hard to measure because it will be very small. Trace rho squared will be very small. So I wasn't planning on talking about this, but you know, the way you measure this is you have multiple copies of the system and you interfere them in some way with a quantum coherent operation. And then you make a measurement, and the probability to get the measurement outcome, say plus or minus, is proportional to 1 plus or minus trace rho squared. And so if trace rho squared is very small, you need to flip that coin many, many times to get an accurate estimate of the probability, the bias, and that would tell you what the entropy is. But what this is saying is that actually there are states where if you did that, you could find that trace rho squared is very small, or some modest thing in terms of the system size, but actually the binomial entropy is very large. And one mathematical consequence or related fact is that the binomial entropy has a nice continuity. So if you change the state by a little bit, the binomial entropy can't change too much.
Good.
But there's no such inequality for S2.
Good. Thank you.
Yep. Okay, let me give you one more example. So now let me have a Hamiltonian H for this example. And let me consider this Hamiltonian to have a set of energy eigenstates, En, and energy eigenvalues, En. And I'm going to consider two copies of this. So I'm going to consider a quantum state, psi AD, which is called the TFD, stands for thermo field double, some old nomenclature, which is defined as follows. You sum over all the energy levels of the square root of the Boltzmann distribution times En on A and En on B. What is this state? Again, it's called thermofield double state. It plays a special role in many contexts because if you compute rho A based on this state, you'll find that it's e to the minus beta HA over Z. So it's thermal. So the thermofield double is like the minimal entangled state, the minimal environment that you have to couple your system to exactly produce thermal equilibrium. And here, this V, which depends on beta, is trace e to the minus beta H.
Here HA means what?
H is just any Hamiltonian. Just pick a Hamiltonian, whatever your favorite Hamiltonian.
And the trace B.
Whatever you want. And I just take that data and I construct this quantum state on two copies of the system.
Okay.
You can always do this, just given this Hamiltonian data. And this is just a generic construction of an entangled state between two copies that when you trace out one half of the system, one of the copies, you get exactly thermal equilibrium. So in other words, if you wanted to interpret the entropy of this state, thermal entropy, as entanglement, you could do that provided your system, your composite system within this quantum state. And here I just want to point out that trace rho A to the alpha can be written in the following way as Z alpha beta, Z beta to the alpha. And this quantity, I'll say, can have funny dependence on beta. What is Z? Z is a partition function. So it's basically equal to the exponential of the free energy. That means that the system is undergoing a thermal phase transition at some temperature, then this Z will be a singular function at that temperature, right? Depending on the first order transition, second order transition, etc. So this is calling in your statinic knowledge. And what you see here is that if, say, you're interested in trace rho squared, the Renyi entropy, that involves both Z at beta, but also Z at 2 beta. 2 beta is a cooler temperature. And so that means you take the thermal equilibrium state at some hot temperature, T hot, and the Renyi entropy knows about the equilibrium properties at a cooler temperature, T hot over 2. And so even if T hot is not near a phase transition in temperature, T hot over 2 could be. And so what you see is that actually this quantity, this Renyi entropy, knows about the physics of equilibrium at different temperatures, at cooler temperatures, right? In particular, it can have singularities as a function of temperature where the actual density matrix or actual observables that you would measure in the lab don't have singularities. So this Renyi entropy is really, it's a very fine-grained property of the quantum state. It's not something you can access easily from measurements on one copy or incoherent measurements on many copies. It's really a very fine-grained thing. Nevertheless, it's computable and it's accessible, and so we spend a lot of time thinking about it. Even though I would say as theorists, or as a theorist, we would very much like to be able to compute the von Neumann entropy directly. Any questions about these examples? Okay. Well, let's talk about some more examples now of dynamics. So now at last we're coming after about 40 minutes of setup. We're coming to our first look at the actual structure of the actual phenomenon of interest here. And again, I'm just going to go through a series of examples to help you build some intuition. So suppose we start with a state psi AB, and it evolves into a state which is related to the original one by unitaries acting on just A and just B. And let's suppose I want to compute delta S, which is equal to the change in entropy of A. In this case, you have the result that delta S is identically 0. In other words, the entropy is invariant under unitary rotations of A and B separately. If you like, you can think in the Schmidt way of describing this quantum state psi AB, what UA and UB do is they rotate the Schmidt basis, but not the Schmidt values. And the Schmidt values are what determine the entanglement, these different entropies. Okay. Now another example is the following. Suppose we take psi AB and we evolve it with a general unitary which couples the two of them. In this case, what is delta S? Well, of course, it depends on the unitary. And so what I can give you is a bound. Delta S is less than or equal to the log of the min of the dimension of A and the dimension of B. So basically, it can't increase by more than the minimum between A and B of the dimension. And this bound is saturatable because you can go from, say, I equals 1, I equals 1 on A and B. There exists a unitary U which will take this to some I equals 1 to N. And it's not hard to make this sort of unitary.
Can I ask a question?
Yeah, please.
If I consider one of these two systems to be infinite and the other one to be finite, does this formula still hold?
Yes.
Okay.
If you go back to the Schmidt basis, to the Schmidt decomposition, the way I think about this, or the way I think about it, is to say you never need more than the complete basis of each side. And so whichever of those two is the smaller is sufficient, right? So in other words, if you have like a single spin coupled to a quantum field theory, well, there's the state the field theory is in when the spin is up and the state when it's down, and that's sufficient to tell you everything. The field theory state can be arbitrarily complicated, but kind of as this example indicates, it doesn't matter how complicated it is. On the subpiece, it just matters how much correlation it's between the two. Okay, now let's do a slightly harder case. This is what's called ancille-assisted dynamics. And now the idea is the following. I have a little auxiliary space little a space big A, a space big B, and an auxiliary space little b. And I have a quantum state on all these things. but it evolves by a unitary acting just on AB. So I have a bigger space on A and on B, on the A side and the B side. And I don't say anything about what the state is within that bigger space. And I want to know what is the change delta S of A. Right, so this is a subtle but important difference. In the previous case, I was allowing the unitary to act on the whole system that I was considering the entropy change of. Now I'm considering the entropy change of a bigger system, but the unitary can only act on a subsystem of that, on bigger. And this is not clear. Like, is it just the same as before? Is it just that the bound, say, is never more than log of dimension of A or dimension of B? Or could the dimension of little a come into it in some way? Can little a affect even though it doesn't act on little a? And it turns out that you have the following bounds, which one can actually prove relatively easily using some entropy inequalities, that this delta S A is less than or equal to 2 times the log of the min of dA dB. So there's this factor of 2. And let me show you a cartoon for how this works. Suppose A and A are in an entangled pair, and B are in an entangled pair. So dA equals d big A equals d big B equals d little b equals n. And this indicates the maximally entangled state. So little a and big A are in a maximally entangled state, little b and big B are in maximally entangled state. And now what I want to do is apply a swap on A and B. So it just exchanges those two states. That's a one unitary operation you can do. You can just exchange two systems. What does the picture look like afterwards? Well, now it looks like this. Because I just exchanged A and B. And so before I had no entanglement. Afterwards, I had 2 log n entanglement. So it can actually help. You can go faster with these auxiliary systems than you could with that. You can generate more entanglement. But this turns out to be the upper bound. You can never do better than this. And again, you can saturate.
So the bound has no dependence on little a. Like, should we expect that to be the case? Or
it's true, it's not dependent on little a. And I would say a priori, you should not expect that to be the case necessarily. Like if you just encounter this problem in the wild, I wouldn't necessarily have a strong prior. But this turns out to be the situation. And let me just say, like, the way you can, this is an aside, the proof of bound for von Neumann entropy is based on 3 facts. Fact 1 is that the entropy of, let's call it X and Y, is less than the entropy of X plus the entropy of Y. This is only for von Neumann entropy. This is called subadditivity. You also have this, XY is bigger than or equal to the difference. And then 3, you need the unitary invariance. So you can consider something like S A B initial minus S A B final, and this is equal to 0 by unitarity. And then you need to apply these first two rules in a clever way. So this is a good exercise. Try to prove the bound. But those three facts are sufficient to do it, I think. All right, let me give you one final example, which is Hamiltonian dynamics. Let's suppose, again, you have the same kind of setup, A, B, B. You have a Hamiltonian, which is something within the A part, something that couples, and something within just the B part. Then we have a result called the small incremental entangling theorem. It's a conjecture until 2013, but it was a theorem after that. This is due to again, if you look on my page on the wiki, I have the actual archive link, so you don't necessarily need to copy this down, but it's there. And it says the following: dSA dt is less than or equal to some universal number C times a suitable norm of the coupling term times the log of the min of dA and dB. So we have our familiar cast of characters. We have some constant here. We have log of the dimension. And then this norm is called the operator norm. And it's just a measure of how big the Hamiltonian is, right? Because obviously if I take a Hamiltonian and I double it, then I double the generation of entanglement. I just double the rate. So how big the Hamiltonian is, it has to come into it somehow. And this is how it comes into it. But you'll see again, it does not depend on the dimension of A and of little a and on little b. And so what was hard in 2013, what they accomplished in this paper, it was known this was true when you don't have the little a and a little b. And what they were able to do is show that in the case where you do have a little a and little b, then this still holds. Okay, so that was kind of the advent there. And again, it's only true for alpha equals 1, which is the von Neumann entropy. And you can extend it to multiple terms via Trotter composition. Don't worry about the details of that. Just if you have a sum of different couplings, then you can go term by term and down. So any questions about those examples?
Yeah, I had a question. Can you write down the same formula for the B system? So ds little b big B dt?
Yeah, it has the same, exactly the same form.
Okay.
And moreover, I may not even said this, but the entropy of A is equal to the entropy of B when AB is in a pure state. This is like, there's like a zillion factoids about entanglement, about these entropies that, I don't want to just bore you by listing a million facts. But this is an important one, so let me just mention it.
Sorry, can I ask a question?
Yeah.
So I have a question about the theorem you mentioned in the previous slide. Do we have any bounds on the universal constant C in the theorem?
Yes, we do. It's just a number. It's like it's less than 4 or something.
Oh, so we know what number it is.
Yeah, we know a bound on it, and I can't remember what the current state of the art is in terms of the best possible bound, but for most purposes, you know, just the fact that it's a number independent of H and dA and dB is sufficient.
Thank you.
One thing I will comment on here is that you'll note that this does not depend on the state at all. I didn't assume anything about the quantum state. So you might hope that if you have some information about the state, you can get a tighter bound. And that is indeed true in many cases, but this is like a totally general state independent bound, holds for any Hamiltonian, any system, any quantum state. And yeah, this is just the aside that I said, SAB is equal to SB, SA is equal to SB, basically because they both depend on the Schmidt values in the same way. So that's a useful fact. So now let's talk about the actual phenomenon. Okay. So I want to consider a system of n qubits. So n two-level systems, n spin halves. And I'm going to consider these qubits to be arranged in a line like this. There can be a lot of them. And the Hamiltonian, I'm going to take a Hamiltonian for some dynamics, is going to consist of a couple of terms. The first term is a coupling between nearest neighbor spins and the Z bases. The second term is a magnetic field in the X bases, and this third term is a magnetic field in the Z bases. So this is a nearest neighbor coupling. You could think of it as like something here. These are effectively magnetic fields. Which point in some direction. Let's see. Like that. Sigma or alpha is equal to the Pauli matrix for qubit slash spin R. And so I'm using sort of magnetic language here, which comes from my condensed matter background, but this is just a way to interpret it. It's a perfectly well-defined Hamiltonian, which couples these different degrees of freedom, in which this term represents a coupling that favors neighboring spins to align the Z bases, but doesn't care what direction. This term wants the spins to align the Z basis along the field HZ, and this term wants them to align along the field HX. And because the X term here doesn't commute with the Z term and this Z term, this is a non-trivial quantum mechanical Hamiltonian, and it generates some non-trivial dynamics. In fact, this Hamiltonian for generic JHX HZ is what we would call quantum chaotic. And all the interesting mysteries of quantum chaos is a lecture for another day. But for our purposes here, what this will mean is this Hamiltonian, among other things, if you start out in some out of equilibrium state, will effectively approach thermal equilibrium. Right, so it can serve as its own heat bath, even though it's not coupled to any external world. Any questions about the setup for this thing? Many of you may never have seen a spin Hamiltonian on a chain before. It's called a spin chain, but it's I think not too complicated. If you have n qubits, a 2 to the n dimensional vector space, and you have a series of terms that couple neighbors and have one side.
I have a question.
Please.
So these couplings, are they random variables?
Nope, just the fixed number.
Okay.
We could make them random, and that's interesting. And I'll actually supply, I'm going to show you a figure in a second of the entanglement. I'll actually supply some code if you want in MATLAB to generate that yourself. You can mess around with, or you can try to mock it up in some other language. But yeah, it doesn't, it's not random here.
Okay, thank you.
Are we restricting to j greater than 0 for the ferromagnetic interaction?
Yeah. So let's do the following things. The initial state will be plus y, plus y, plus y for every spin. And why I choose y? Well, the expected value of x and z in the y state is 0. So the expected value of that Hamiltonian in this state is 0. And if that means is that actually it's at the middle of the energy spectrum. So if you plot out the spectrum of energy levels of that Hamiltonian, it goes from some negative value to some positive value, with most of the states at energy 0. And this is a state, this is one state at that 0 energy sector, which, as we'll see, corresponds to thermal equilibrium, or corresponds to an infinite temperature final equilibrium state. And here I'm doing n equals 14 qubits. And I'm looking at entropies of either, say, 1, 2, or 3, etc. systems at a time. So this is L equals 1. This is L equals 2, L equals 3, and so on, up to L equals 7. That's half the system.
These periodic boundary conditions?
No, there's open boundary conditions.
Okay.
So what do we see here? Let's look at this. This will be the final thing for today. What do we see? We see a couple of things. So first of all, entanglement all starts at 0 because this initial state is unentangled. So check, that makes sense. Second of all, we see if we go out in time, at late time, entanglement has some final values, and it's independent of time. So the entanglement saturates something. We'll come back to what that something is in a second. Third, you can see that at early time, relatively speaking, the entanglement grows approximately linear in time, until at some point when the entanglement of each subsystem gets close to its late time value, it starts to peel off from this curve, peels off, peels off, peels off, and approaches this asymptote. So in other words, all the regions have constant entanglement growth until they get close to saturation, in which case they peel off from that growth curve and approach saturation in some way. Right. But the rate is actually the same for every region, at least initially. So all the regions coincide until they start to peel off as they approach the saturation. The saturation itself, what are these dashed lines? What I did was I took just a random vector in the Hilbert space. So this is a 2 to the 14 dimensional Hilbert space. I just chose a random vector. I asked my computer to give me 2 to the 14 times 2 random numbers. And I use that to make random real parts and random complex parts. I normalized it, and I compute the entropy of that thing. Just a single shot. That's what these dashed lines are. And so what you see is that at late time, entropy is approaching that of a completely random state in the Hilbert space.
Brian, you have 5 minutes.
All right, great. In particular, if L is less than, let's say much less than And over 2, the entropy of L is approximately just L, which is maximal. So subsystems, let's say small subsystems, look maximally mixed, which is what you'd have in thermal equilibrium at infinite temperature. I see a question about whether the early bump has any physical meaning. It certainly does, but I would say it's a non-universal meaning. It depends on the Hamiltonian you've chosen. So like at very early time, the Hamiltonian, can have oscillations essentially, because it's just rotating, it's processing magnetic fields and rotating ferromagnetic couplings. And so this kind of very early time wiggles are characteristic of the Hamiltonian, but they don't necessarily, have any universal meaning across all Hamiltonians, right? And their value will depend on the details. So to summarize, what we see here is we have this chaotic system. It starts in a product state. It evolves at very long time so that it looks like it's an equilibrium. That's one essence of quantum chaos. That's part of the reason why we call this a quantum chaotic Hamiltonian. And that growth has various features. It has an early time non-universal part here. It has an approximate linear growth for a while. It has a saturation, an approach to saturation, and a final saturation. And the late time values are determined by some essentially equilibrium physics, which has to do with how big the Hilbert space is and how big the subsystem is. So this is a phenomenon we want to understand. This is what we'll actually talk about in the remainder of these lectures. And the kind of questions we would like to ask about this phenomenon include: what sets this rate of growth? What does it depend on? How do I describe these saturation parts of the curve as I approach the late time value? What sets the late time value? How long does it take to get there? Are there bounds on these different dynamics that depend on the state, for example? So there's a whole variety of questions that we want to answer. We can generalize this to higher dimensions. We can consider more complicated kinds of models. And that's going to be what occupies us for the next several lectures. So what you can expect next time, I'm going to talk about models and techniques just a little bit, just a very high level overview. And then we'll dig into an effective field theory, essentially, which captures this behavior and makes a lot of predictions about what you would expect for saturation time, growth rate, etc. And we'll sort of play with that in 1D in various contexts. Okay, so that's what you can expect next time around. And I'll also post these notes on the wiki once we're done here. So thanks a lot.
Perfect, thank you. Perfect timing. Okay, questions for Brian?
I have a question way back about the discontinuities and the Renyi entropies. Okay, so for like my whole graduate career, I've been hearing the lore that Renyi entropies are discontinuous, and I've been, even writing it in papers. But I was just thinking about this. The second Renyi entropy is a log of a sum of squares, which sure looks continuous to me unless all of the eigenvalues are 0. So what's going on there? What's missing in my intuition?
Let's see.
The eigenvalues are certainly vary continuously with the trace distance.
Yeah, I think so let's see, what can I say? Well, so one thing to note is that silly example I showed you, I was playing with a 0 eigenvalue initially and then making it non-zero. I don't think that's really the source of it.
Yeah, that would make sense for me if you were looking at a non-integer Renyi entropy, because then you'd end up with, weird square root factors or things like that.
Yeah, I guess I'd say something like the following. So trace rho squared is continuous. Like if if you have two states that are epsilon apart in trace distance, then trace rho squared will never change by more than like epsilon. But part of the issue is that both of them can be very small. And so it's actually kind of a weak bound. And somehow what you're seeing here is that, or what you're seeing in that case is, yeah, what's the best way to say it?
It sort of
Like,
sounds like we're seeing.
There is a Lipschitz constant, but it's just very bad.
Yeah. Okay.
Maybe that's the
It's continuous, but with a massive first derivative or something.
Yeah, that's right. That's right.
Okay.
Other questions?
Can I ask a quick question?
Yeah, please.
So when you were discussing the evolution of those four systems, you know, little a, little b, and big B.
Yeah.
And you discussed two examples, and in both of those cases, the maximum entropy change is limited by the minimum dimension of the AB system, right?
Yeah.
Why? Can you help me to understand why is it the minimum, not the maximum of the dimension of the two systems?
So yeah, great question. So yeah, this has to do with, like, if you go back to the Schmidt decomposition, say, you never need more than the smaller number, like the smaller dimension, right? If we go to our field theory example, like you have a spin entangled with a field theory state, right? With the whole rest of the universe. You just have the amplitude for the spin to be up and the universe to be in some state, plus the amplitude for the spin to be down and the universe to be in some other state, right? So it's the smaller of the two that determine how many possible amplitudes you have.
Okay.
And that's why this min appears. So basically, if you're coupling like a small system to a very big system, it just means that you can't really use most of the big system to make entanglements, because your small system can only couple realistically, you know, sort of physically to a small number of degrees of freedom inside that bigger system.
Mm-hmm.
That's going to be intuition. Is that, but most of it is wasted essentially unless they have the same size.
Okay. That makes sense. Thank you.
Okay.
And I had another question regarding the picture that you showed at the end. So you mentioned something about this system being chaotic. Now,
Yes.
I mean, in you know, if I think about the classical chaos, the whole chaos comes from the fact that the system depends very sensitively on the initial state. Does that also show up here, that if you change the initial wave function a little bit, then the things don't, you know, follow the same kind of nice behavior?
Yeah, this is a good and deep question, and something that people in quantum chaos discuss to this day. The sort of simple answer is that the Schrodinger equation is linear, so small changes in initial quantum state don't grow. But that's actually also true classically if you think about the Liouville equation. So if you shift the initial distribution a little bit, that shift in sort of full distribution space doesn't grow with time. It's just linear, right? That's what the Liouville equation is. So instead, it's really observables that grow in some way, essentially, which can be, if you like, nonlinear. And so for some quantum systems, there is a notion of exponential growth analogous to the classical case. For this spin chain, as far as we know, there's no such notion. So we need to look somewhere else to define what we mean by quantum chaos.
Okay.
And this is an ongoing discussion in the field. So, you know, classical chaos has a set of things associated with it, of which this butterfly effect is one of them. It's not always possible to have that in a quantum chaotic system for various reasons. But there are sort of related set of phenomena. For example, one common characterization is that a system is chaotic if you look at the energy eigenvalues, and if they look like those in a certain precise sense of a random matrix. So they're structureless or featureless in a certain precise sense. And that's one definition of quantum chaos, and you can try to relate that definition to other notions like the entanglement should grow, that you should reach equilibrium, that correlation should decay, etc. Right, and that's part of the struggle of that field to understand how to relate these various notions.
So I mean, the thing that you mentioned about the random matrix, is that why if you just choose a random matrix in your when you are coding the system, and then if you try to compute the entropy, the final entropy, it always gives you the saturation, you know, where the system ends up for higher values?
Yeah, it's related. Like if this Hamiltonian here were not this nice local thing, but if I just chose a random matrix and, you know, a random 2 to the 14 by 2 to the 14 matrix, then yeah, what you find is that entanglement just generates super fast for every region.
Mm-hmm.
You know, of course, it depends on how we normalize things, but essentially there's like no locality, there's no like growth period, it just becomes maximally entangled instantly, basically. And that's one way to understand this late time value.
Okay, and that's somehow relates to the system being chaotic. I mean, is there a connection?
They're different things. So like, you know, when we say that the energy levels of this Hamiltonian are chaotic, we have to sort of be careful what we mean by that, because obviously like the ground state's not, it's a special state. And at finite time, we know about locality, etc. So there's a notion of a time scale called a Fowlis time. And it's like saying, if you look at energy levels closer in level spacing than this inverse time, then they look random matrix-like. And so what we said is we need to like wait for a system to evolve for a long time. So for example, if we wait long enough so that every subsystem is thermalized like this, that's a time proportional to system size. And then maybe after that time scale, the eigenvalues that are more closely spaced than that could look random matrix-like.
Okay, thank you.
Yep.
Other questions, discussion? Okay, so it's a good time to wrap up. So let's thank Brian again.
Yeah, thanks.